Welcome. This is a series of videos that will try to explain in the simplest way the tool called MPLAB Harmony from Microchip Technology to create and integrate code for its 32-bit microcontrollers. Since this is a rather extensive topic, I have decided to divide it into several parts. In this video I will talk about two topics. First, a general explanation of what MPLAB Harmony is, and a second part, trying to understand what an embedded system is and essential concepts for its efficient design. Personally, I think that this second topic needs to be explained before continuing to explain in a little detail what MPLAB Harmony is. MPLAB Harmony is a tool for generating code and libraries for 32-bit microcontrollers, which allows you to speed up the development of a project. The generated code is not just bare metal, since there is abstract code divided into layers, meaning that it is not necessarily written at the microcontroller register level. To generate code, we can use other tools, such as MCC or MPLAB Code Configurator. The Harmony concepts that will be briefly mentioned are application layer, common system services, middleware, device drivers, libraries for peripherals. The application layer refers to the code that the programmer writes to develop a project. As highlighted in this image, there may be several applications, which are specific tasks, which generally manage or control a peripheral or subprocess. For example, one app is dedicated to sending and receiving data through the UART module, another processes that information, another manages a parallel port for an LCD display, etc. Each of the applications should be as independent of the others as possible, and their processes should interfere as little as possible with other apps. Since this layer does not interact directly with the hardware, it is portable, meaning that the same code can be used for a different microcontroller and with few or no changes. It should work without problems. Common services are libraries that manage resources shared by multiple drivers, other libraries, and modules. They can interact with a real-time operating system, or RTOS, through the operating system abstraction layer, called OSAL. This layer is also accessible to drivers and middleware, facilitating integration and interoperability. Middleware allows you to manage complex peripherals that usually have many configuration and initialization registers, as well as many steps to send and receive information. For example, the USB module or the Ethernet module. The application layer can bypass this layer when a peripheral is not very complex to manage, such as the UART module. Drivers are libraries dedicated to managing microcontroller peripherals, providing a consistent interface for their configuration and use. Each driver can have multiple instances, allowing to manage several peripherals or modules of the same type in a project. Configuration includes common parameters between instances, along with specific options for each one, depending on the requirements of the peripheral or application. Peripheral libraries, as their name indicates, allow you to configure the characteristics of peripherals. For example, in a UART module, you configure its speed, the number of bits, parity, interruptions, etc. This allows you to hide many details from the eyes of the firmware programmer, but that does not mean that the programmer does not know how a peripheral is calibrated and works, which is why you should read the information provided by the manufacturer about the configuration and handling of the peripheral. The definition of a system is a complex thing. There are many explanations and all of them seem to be correct. I prefer the one that says that it is a conceptual or real object that is designed to solve a problem. To better understand what an embedded system is, I propose the following mental exercise. Let's imagine an adjustable and programmable voltage source, represented by something similar to the diagram shown in this image. It is important to note that this is just a mental exercise. The example presented is not perfect, so it could lack some important elements or include unnecessary details. The source consists of the following parts. LDO regulator, responsible for stabilizing the input voltage. Resistor array. The regulator uses an arrangement of two resistors, one of which is adjustable to obtain an output voltage that is also adjustable. In this case, the adjustable resistor is controlled via SPI serial communication. Calibration system. Since this is a programmable source, the user calibrates both the voltage across the load and the maximum current that will flow through it. This can be done using electric potentiometers or some type of adjustable dial that generates pulses. Display allows the user to calibrate and view the voltage and current parameters in real time. Sense resistor and amplifier. A resistor, together with an amplifier, is used to measure the current flowing to the load. Protection relay allows the load to be quickly disconnected from the source in the event of overcurrent or overvoltage. The resistor array also allows the voltage across the load to be measured indirectly. Each of these components is managed and controlled by a microcontroller, and each part must be handled in a coordinated and efficient manner. So, the processes or tasks that the microcontroller must perform are the following. Measuring the current that flows through the load, to disconnect the relay in case of overcurrent. Measuring the voltage on the load, to adjust the value of the SPI resistance. Reading the dial to calibrate the maximum current that will flow through the load. Reading the dial to calibrate the voltage that must be on the load. Managing the display. Each of these processes or tasks must be modular, meaning they must be as independent as possible from each other. In this way, an error can be corrected or an update can be made without affecting the other task. Another advantage of modularity is that each task can be assigned its development and maintenance to different programmers, and each one would work independently without interfering with each other. To achieve this goal, a task scheduler or preemptive multitasking processing is used. The proposed source control is a concurrent system, since there are several processes or tasks that overlap or superimpose one another. For example, while the value of the SPI resistor is modified, the current that flows through the load is measured and monitored. It is also a deterministic system, since it must produce the expected results, that is, there is no randomness in the voltage or current in the load. It must have synchronicity, since each task must do a part of all the work, but at the same time, they must allow others to be executed. That is, they must take turns to complete the entire process. A concurrent system is not perfect and has the following characteristics. Latency is not constant. For example, the time it takes to reach the desired voltage on the load depends on several factors, such as the type of load and its current consumption. This is an external factor to the system, and this type of latency is called jitter. On the other hand, when it is an internal factor that increases latency, for example, the CPU must execute a task that was idle, and especially if it is a high priority, it is called throughput or increase in workload and decrease in performance. If any latency increases to a very high value or there is never a response to a task, the system enters into what is called a deadlock, and is what is commonly called a hung system. An example of this could be, assuming that there is a disconnection in the SPI bus of the adjustable resistor, the microcontroller code could remain in an infinite loop waiting for the resistor to respond to the commands sent. Tasks can have priorities. A higher one can interrupt and pause another. In the imaginary example of the voltage source, the task that measures the current has the highest priority, and in case of an overcurrent, it should not only pause the others, but also stop them. Open the protection relay and inform the user of the problem on the display. The assignment of priorities and the control of them is called the mutual exclusion algorithm. It can be said that the example of the adjustable voltage source is a concurrent system because it meets the following characteristics. There are actors that carry out the automation process, that is, tasks, threads, code routines or processes. There are resources shared by the actors, that is, the CPU, memory, registers, and they could even be some peripherals. There are rules or norms that control the processes, such as synchronization or task priorities. Deterministic results are produced, that is, expected or desired result. The problems that a concurrent system can have are the following: race conditions, incorrect or poorly designed synchronization method, poorly designed mutual exclusion method, starvation, deadlocks. A race condition occurs when two or more processes access a shared resource. This is best understood with an example. Imagine that two buyers are searching for the same product on a store's website. There are only 5 units of the desired item in stock. One buyer wants to buy 4 units, and the other wants to buy 3 units. Both make the purchase at the same time, but the system first serves the one who wants 4 units, and then processes the request of the one who wants 3 units. The first buyer will be happy, because he will see that his 4 units will soon be shipped. The second buyer will see that only 1 unit will be shipped, even though he bought 3 units. And the store manager will see that in the inventory, a negative number in stock. This example is a race condition and is a problem that should not have happened. Race condition is a bug that is often difficult to fix, as it occurs infrequently and is not repetitive, which is why it is often called Heisenbug. The solution to this problem is to use synchronization method. The first method is called mutual exclusion or mutex. A flag is used to inform that the process is busy. The process becomes an atomic operation, meaning it cannot be divided into more sub-processes or interrupted until it is finished. The second method is to use semaphores, which is similar to the mutex, but the process remains paused until it can be continued. The programmer does not have to worry about trying to perform the process again or waiting for it to become available. This means that the task or process is handed over to the semaphore and it is responsible for performing the process when the shared resource is available. Synchronization can cause some problems, for example, starvation, which happens when a task is almost constantly rejected when it wants to perform a process, because that process is occupied by higher priority tasks. This problem can be temporary, but it decreases the performance of the system. Deadlock happens when a task cannot exit or finish from a shared resource. For example, if you forget to clear an interrupt flag in the microcontroller code, that exception happens again and the main thread is never returned to. Using the watchdog timer could help solve a deadlock, but it is a cumbersome solution. No robust system with properly designed code should resort to the watchdog to solve that problem. A microcontroller can create recurring processes because it typically has the following resources. Interrupts, either single or multi-level, allow the creation of preemptive multitasking processes. In this case, the normal flow of code is interrupted and paused while other code related to the interrupt is executed. The context needs to be saved before executing the interrupt code. The context includes the accumulator and other shared registers that were being used in the previous code before the interrupt occurred. Parallelism refers to the division of code into small parts that take turns with each other. This can be achieved by using state machines, which make it appear to the user that the microcontroller is running multiple processes at the same time. However, to achieve true parallelism, more than one CPU is needed. Typically, a microcontroller has only one CPU. Cooperative parallelism is when a peripheral helps the CPU by relieving its load. An example of this is the UART module, which is responsible for sending or receiving each byte of data. This process is performed by the peripheral, not the CPU. Independent core peripherals is a concept similar to cooperative parallelism, but the peripheral performs much more complex tasks, such as mathematical calculations, and can even send the processed information to other peripherals without the CPU performing any additional processing. A task scheduler has the following characteristics. It helps the CPU to avoid performing redundant tasks, or waiting for a response or result in an infinite loop. It prevents the programmer from using only interrupts to create his code. It allows tasks to access the CPU equally, avoiding competition between them. The scheduler can be of three types: cooperative, preemptive, and a hybrid, which is a mix between the two previous options. As mentioned before, cooperative processing consists of dividing all the code into subprocesses, also called threads. When a thread finishes, the CPU executes the next thread. This is best understood in state machine-based systems. It is useful for low and medium priority processes. It is the way many MPLAB Harmony examples are designed. In a preemptive task process, the scheduler is the one who decides which task is executed, which means that one task can interrupt another. It is a more complex process and requires a lot of resources for its stability, in addition to the fact that each task contains its own context, which implies a greater use of RAM memory. Variables shared between tasks must use mutexes or semaphores to access them and avoid race conditions. This method is the one used by most real-time operating systems, or RTOS. This method should be used in processes that have medium and, above all, high priority. There are different types of schedulers and I will not talk about them in detail, but I will mention some such as the sequential task scheduler, round-robin or RR, the basic priority scheduler, the advanced priority scheduler, the scheduled task planner, the task queue planner, the planner in states. And the latter is represented in the image on the right and is basically a state machine. This is the end of this video. It was essential to understand these basic concepts of an embedded system as a starting point. In the next video, we will go deeper into MPLAB Harmony and its practical application.